I was asked to discuss with you about exoplanets and habitability. And actually, we could have this discussion without using the word habitability, because I'm a physicist, I'm not a biologist, and mainly I will deal with liquid water, and not every kind of liquid water, surface liquid water. And although it's quite easy to find a chemist or a biologist like Hervé saying that liquid water is essential to life as we know it, well, it's more difficult to argue for liquid water. And so why is, for surface liquid water. So why is surface liquid water so important? Why is this habitable zone we are going to discuss interesting at all? And these are the kind of things we are going to discuss. So habitability is a word that has, let's say, that has been used in our community for a long time. It's probably not the appropriate word, and you could suggest better ones, but let's see why we are interested in that. So usually habitability means where life can be, where life can exist. I mean, that's the most simple approach you can say. But in a more practical way, it's also where we can find it, because we can discuss forever whether it's possible for life to be somewhere. If we cannot check if it's true or not, well, it will remain a theoretical possibility. So there is a more practical route to that, which is to say, well, habitability is where we can find life. And then, if it's the approach you're choosing, it will be very different whether you're discussing this within the solar system or for other stars, other planetary systems. Why is that? It's because, well, in the solar system you can go there. You can dig, well, maybe not now, but within the next decade, we are going to explore planets, we are going to dig, we are going maybe to probe, to sample oceans of icy worlds in search for, I don't know, prebiotic chemistry or even life, why not? But when you deal with extrasolar planets, probably for decades, probably more for centuries, and before we can think about some kind of in situ exploration or sample return mission, we will have to study them remotely. So it's not the same approach, and many people will tell you, well, we are interested in planets that can harbor surface liquid water because we want to be able to see it from the distance. That's saying that, I would say, intuitively, but we can do, I think, better than that. So I think there is a link, a strong link between what we call the habitable zone, which is the region where planets can have oceans, if you want, at the surface, and the quest for signs of life, remote signs of life. So usually the main criticisms against habitable zone, it's people working on solar system bodies saying, well, we are interested in life in icy moons of Jupiter and Saturn. So these are really not inside the habitable zone, and we are still interested in that. So why are you introducing this concept of habitable zone? We can have planets that are outside the habitable zone and that can have internal oceans. And there is no argument to forbid life to be there, and that's true. But you may have arguments to say it will be very difficult to remotely find internal life compared to life that grow at the surface. Why is that? So first of all, let's take the example of the Earth, which basically, it's by looking at our planet that gave rise to this idea of being able to remotely find life elsewhere. We don't know if it's true, but it's just by looking at our planet, because if you look at the spectrum of our planet, here in blue, so here you have the reflected part in visible and in infrared, and here you have the mid-infrared spectrum, and you have the Earth, Venus, and Mars. Only on the Earth you will find signatures like molecular oxygen and ozone that we know are produced by life on our planet. On Earth, we know that these are byproducts. Oxygen is a byproduct of life, and ozone is a byproduct of having an oxygen-rich atmosphere. And this is due to life, and this is due to this process known as oxygenic photosynthesis that was invented at some point by life, and that allows life to use the hydrogen contained in water to reduce the carbon contained in carbon dioxide using the energy, quantum energy of photons, to produce organic matter. And in the process, it gets rid of this oxygen. And this you can see from the distance by using telescopes and spectroscopy. And this is the result of some very, I'm not a biologist, but this is the result of some very, very, very complex systems called photosystems that allows life to use directly photons to store their energy and to use them to make the process that was summarized in this very simple formulation. So this is for oxygenic photosynthesis. There are other photosyntheses. Not all of them produce oxygen. Not all of them use water. But these kind of things allow life to use light from a star that's much hotter than the Earth. So if you look at the Earth and you look at the amount of light that we receive from the sun, so if you get rid of, if you count only the light that arrives at the surface of the Earth, it's this amount. And about 0.15% of that is directly converted by photosynthesis into chemical energy, into making organic molecules. On the other hand, you have life that doesn't do that doesn't use light, and that use other processes, and that will eventually have to rely. So either it has to rely on products of photosynthesis, like for instance, you have a lot of methanogens that use the organic matter that's produced by photosynthesis, but you have some microorganisms that can use very basic things that are not produced by life, and they rely on the internal heat flux of the Earth. Not directly, and we will come back to that, but so this is, in average, the heat flux that arrives at the surface of the Earth, and about 1/1,000,000th of that is, less than 1/1,000,000th of that is converted into some kind of chemical energy by life. So basically, if you compare the primary production that links with photosynthesis, it's about 200 grams of carbon per year and per square meter, while if you compare the amount of organic matter that's produced by other autotrophic life forms that don't rely on light, it's less than 50 grams per million of years per square meter. So why is that? Well, I'm not a biologist, but in terms of physics, it has quite a simple explanation. It's due to the fact that this energy and this energy have not the same quality. We have a quantity in physics that's called the entropy that gives you an idea of the quality of the energy and how efficiently you can convert it in work. And the light we receive from the sun has a very, very high quality, very low entropy, because it's emitted at a temperature that's very different from the Earth, about 6,000 Kelvin. So it can be used directly as quanta of energy by life. On the other hand, a heat flux that's just about the same temperature of the Earth is very high entropy. It's very difficult to use it to do things. So basically, so that's why I was saying, these photons have been emitted at a temperature that's much, much higher than the temperature we have in our environment, which make them very, very high quality, while actually, in order to use the internal heat flux, you have to use it indirectly. So for instance, if you have some fluid circulation, you will transport things that are not at the equilibrium with our environment, and you will be able to use the redox differences that are produced by these gradients. It's very indirect, and this is why it's very inefficient to use that and to transform it into really usable energy. So, and there was a very nice paper studying these kind of things in 2006, and so by Minnie Crosing and some co-authors, and I was saying that in a world with a purely chemoautotrophic primary production, so without the photosynthesis, the biology will cause no significant effect on the global carbon cycle, at least from what we know on Earth. And this may be an explanation why, although chemoautotrophy is known for a long time, more than a century, it was really, I mean, the biosphere using that was really unveiled in the 70s, in the 80s, because basically it doesn't do much. So it's very difficult to find it and see it. It's there, it exists, it's some very significant forms of life, but it doesn't do much in terms of the Earth. So basically, this comes to this idea that, maybe wrong actually, we shouldn't have any confidence, too strong confidence on that, but it's an idea that the habitable zone where you can have liquid water at the surface is interesting because there you can have simultaneously liquid water and light from the star. That could give rise of some photosynthesis produced. It doesn't have to be the same as on Earth. It doesn't have to produce oxygen, it could do something else. But this ability to use water and life at the same time, it's something that we believe is important. So habitable zone is not a good word. We agree on that. So during the past years, we suggested different names. I suggested one that is the hunting zone. And it's becoming popular, but now I regret. I don't think it's a nice word, because we live in the habitable zone of the sun, and I don't want to live in a hunting zone. You never know what's waiting for you around, okay? So I don't think hunting zone is a very nice name. So a student of mine, Emmeline Beaumont, proposed the surf zone, which is more peaceful way to understand that you can have waves, so you have surface liquid water. So let's discuss a bit about this surf zone, okay? And basically the kind of things that in my field we are doing is trying, and it's not easy, to define what are the boundaries of this habitable zone where it's not forbidden to have a surface ocean. So although there have been like 30, 40 years of study about that, you can still find in some scientific papers people who estimate this region by doing this very simple calculation of an equilibrium temperature. So basically they consider the flux that's absorbed by a planet. So they take the flux at the distance of the planet, they remove the part that's reflected, and they say, well, this energy is absorbed and it's re-emitted by the planet at a temperature in order to really re-emit exactly the amount that it was received. So this equilibrium temperature. But this works only first if you have no atmosphere. And actually, you need to give a coefficient to this fraction here. It's the redistribution factor. So typically, people use F = 4, which means that the whole planet has the same temperature. Basically, you're transforming a disk into a surface, and there's a ratio of 4 in terms of surface. Or you can really compute locally what's the temperature. Then you will have high temperature at the substellar point, and then it tends to 0 at the poles, and you will have 0, or the temperature given by the internal heat flux in the night side. So usually people use this value, this hypothesis of uniformity, but you understand that if you have no atmosphere, there is absolutely no reason for the temperature to be the same everywhere. So there is a big contradiction between assuming on one hand that you have no atmosphere and assuming that you have the same temperature everywhere, which supposed not only to have an atmosphere, but a very thick atmosphere that redistributes all the heat everywhere. So it doesn't work, actually. This works. It works, for instance, for Mercury or the Moon, at least for the day side. But they have no atmosphere. And here, if you compare what it gives you, so we know the albedo, which is the fraction of light that's reflected by planets. So here it's the value for Venus, for the Earth, and for Mars. This is the value it gives you for the equilibrium temperature, and this is the average surface temperature of this planet. Sorry, it's truncated here, but it works fairly well for Mars, which has a very tenuous atmosphere and a kind of a bit of a lunar climate, I would say. For the Earth, there is a difference of about 30 degrees that is due to greenhouse effect from the atmosphere. And for Venus, there is a huge, huge difference. Okay, so it doesn't work. And why it doesn't work? It's that, okay, we are interested in liquid water, and usually people think of that in terms of temperature. They say, oh, liquid water, we need to have a temperature above 273 kelvins and below the critical temperature, which is 647 Kelvin. Above that, there is no difference between gas and liquids. So usually people have this region in mind, but you have to keep in mind this part, which is the pressure. So at the minimum temperature allowing liquid water to exist, you already have 6.1 millibar of water. And 6.1 millibar of water as an atmosphere, it's already a very strong greenhouse effect. So there is no case where you can have liquid water and neglect the greenhouse effect or the atmospheric effect. So you are trapped. You have to do atmospheric physics if you want to study oceans, liquid water. You cannot just calculate equilibrium temperature, although you will find that everywhere in exoplanet literature. So one way to understand what greenhouse effect is, there are different ways to explain that. This is my favorite. I don't know if it's the better, but so if you have no atmosphere, basically, when you want to calculate the temperature of the surface of your planet, you need to calculate the amount of light from the star that is absorbed. So basically, there is some flux arriving, some is reflected, the rest is absorbed, and then from that, you will calculate the temperature that re-emits that. If you have an atmosphere now, if you have an atmosphere, and this atmosphere absorbs and emits in the infrared, and it has a certain temperature, whatever, it can be low, whatever, it has a temperature, and let's say it's transparent, in this case, it's transparent in the visible or at the wavelength of the stellar light. So let's say for the sun, it's not true, but let's say it's transparent between 0.4 and about 2 microns. You get all the energy you would get without an atmosphere. But in addition to that, you get the emission from the atmosphere. It has a temperature. It has the ability to absorb and emit in the infrared. So you also get the flux from the atmosphere. So when you come to computing the temperature of the surface, not only you have the flux from the star, you also have the flux from the atmosphere. Okay? And where it's quite complicated is that, well, actually, so in order to compute the temperature of the surface, you need to know all that. But the temperature of the atmosphere will be given by the absorption of that. So it's an iterative process. So you have to do some modeling. And you still have to respect the radiative budget of the system. So actually, you can still define an equilibrium temperature. It's still correct. But typically, you will find this temperature physically in the atmosphere in the region of the photosphere, which is where the atmosphere emits. And usually, it's very cold. So on Venus, it's around 230 K. It's about 60 kilometers in the atmosphere at about a 1 bar level. This is where it emits, and it's indeed about at the equilibrium temperature. So if you look at the thermal emission of the Earth, average during 1 year, so it's not completely uniform, but if you look at the thermal emission, and in terms of brightness temperature, most of it is around the equilibrium temperature of the Earth, which is 255 Kelvin. It's not the surface temperature. You don't see the surface temperature here. If you take a 1 month average in a period that's quite dry, for instance this one, you will have some atmospheric windows that let you see the surface and let you see an emission that's much stronger because it's at the temperature of the surface, like here in the Sahara. So sometimes you have windows that show you that yes, the surface it's very high. It was very difficult on Venus to find these windows because they were in the microwave. So you still can define this equilibrium temperature, and it reflects very well the emission of the planet, but it has no direct, simple relation with the surface temperature. And, okay, so the inner edge of the habitable zone, where inside of it you can no longer have liquid water at the surface, it's due to a process that's called a runaway greenhouse that was found in the 70s and described, for instance, in terms of habitable zone by Jim Casting. And it's the fact that at some point, if you increase the flux on a planet that has a water reservoir, at some point there is a threshold where in order to re-emit the energy the planet absorbed, you need to have surface temperature of about 1600 Kelvin, which is enough to melt most of silicates, for instance. So it's huge. So basically, you're getting from here to that in a very tiny change of the stellar flux. You're melting your planet and vaporizing the whole ocean. And this is called the runaway greenhouse. So you can see that you're completely breaking this relationship, this black body relationship, because this would be how a planet without an atmosphere would behave. A very small change in temperature because of the power 4 of the black body flux in temperature. A very small change in temperature, well, allows you to get rid of any little excess of the incoming flux. But when you have water there, it doesn't work. So I made a small animation to try to explain that, and usually it doesn't work. Usually people tell me that, well, we didn't understand. But I keep showing it again. I don't know why. But so I will try to make an effort in making this useful. But so what I did is actually here you have the temperature, and here you have the pressure. So this is the atmospheric profile. So this is the surface, and basically you're getting into the upper atmosphere, and you have the change in pressure. So it gives you the thermal profile of the atmosphere. You can read it here in terms of altitude. This atmosphere, it's made of 1 bar of nitrogen plus some pressure of water that's determined by the surface temperature. And I will increase the surface temperature, which corresponds actually to a distance to the sun, and you will see how the temperature profile evolved. So I will try to, I'm not sure if I can do that. I'm not sure I can stop it, sorry. Okay, my purpose was to stop it and to explain you at different steps, but whatever. So what you can see here, I will run it again. So when you're increasing the temperature, well, the pressure at the surface increases because you can put more and more water. At 100 degrees Celsius, you have 1 bar of water. So you're doubling the surface pressure, and then the surface increase with the temperature. And at this point, it's the critical point of water. So beyond that, you're vaporizing your whole water reservoir, how big it is. And what this point is the region in the atmosphere where the radiation is emitted in space. It's the photosphere. So you can see that at some point, its temperature, it's stuck. It's stuck around 300 K, a little bit less. So whatever the surface temperature, your planet emits about the same. And this is why, at some points, you cannot get rid of the incoming energy by just increasing the temperature. You will have to get to 1600 Kelvin in order to get through this atmosphere at visible and microwave wavelengths. Otherwise, this radiation is stuck into the lower atmosphere. And this is what produced the runaway greenhouse. So the fact that, basically, you cannot increase the amount of emission by increasing the surface temperature. Which is why you have this behavior, and at some point, so you can see the dashed line, you jump from the critical temperature of water to the melting temperature of silicates. And it's even worse because this was the work of 88, and with more accurate spectroscopic data on water, actually, this threshold is getting very, very much closer to the condition we have on Earth. So this is so basically this is what you get if you do 1D simulation of the 1D simulation of a planet. You get this relation between the temperature of the surface and the thermal flux from the planet, and you can see that at some point it's stuck at some value. And this is done by assuming that the atmosphere is saturated. So at the surface, the pressure of water is given by the Clausius-Clapeyron law. It's the saturation of water. But it's not what happens in reality when you have a 3D atmosphere. And this is going to change the story. Two things are going to change the story. The distribution of relative humidity, which is not one. Even if the planet is completely full of water, you have circulation on the planet, and you don't have saturation everywhere. And the second very scary thing for us studying atmosphere is clouds. Clouds is really one of the most complicated. Usually when you say what are the most complicated things in physics, you will say, I don't know, dark matter, magnetic field. Well, clouds are not very far in the list. They're very, very difficult to model. And this is only part of complex processes like convections, turbulence. Of course, you will be influenced by the distribution of continents and oceans and rotation of the planets. So basically, you can run this 1D simulation of an atmospheric column and changing the saturation of the atmosphere. Say, oh, I'm not completely saturated, I'm 60% saturated, or I'm 45% saturated. And you can see that it changed the threshold. And now if you do a climate simulation in 3D, and you see what you get something that's closer to this value. So basically, there are regions on the atmosphere that are quite transparent, quite dry, and that can get rid of energy. That's the same. So basically, if you do that in 1D with just one average column, you will find that the Earth is at the edge of having its ocean vaporized. Like you change by 1% its orbital distance, and bye-bye the oceans. And in terms of time, because of the increase of solar luminosity, this will be, I would say, within a couple of 100 million years. Now, with 3D simulation, which are not a truth, it's just a progress compared to that. It doesn't mean that we are going to make more progress. This gives us a bit more time, like 1 billion years. Because the limits between having liquid ocean and completely vaporized ocean, it's 5% closer to the sun. It's better. So basically, we have this picture where, okay, here we have in terms of flux received compared to the Earth. So 1 is the Earth, and orbital distance in astronomical units, so 1 in the Earth. So we have the Earth here, we have Venus here, and this is the inner edge that's predicted by 1D simulation. And if you trick your 1D simulation by adding 50% of clouds, you will get this limit here. So by using this 3D simulation and by using the same rotation period as the Earth, you will find the inner edge to be here. But now if you assume your planet to be tidally locked, to be synchronized, like its rotation period is the same at its revolution period, so it's showing always the same face to the star, well, there are big uncertainties and models disagrees, but basically you can get your planet with oceans much closer and near the actual distance of Venus today. Well, why is that? It's because when you do that, when you have a really synchronized planet, so here it's rotating in our frame of rest because we want to see all the dark side and the night side. So here you have the albedo and you have the humidity, thermal flux. Actually, so you will have a day side that's much hotter than the night side and a lot of convection and a very, very thick clouds. A very thick deck of clouds covering the day side and making the albedo very high. So this planet is going to reflect a lot of light. A bit like Venus, that has an albedo of 0.7. Not as big, but so actually, it's interesting because having a synchronized planet could make it habitable closer to a star. It's interesting. So we'll keep that in mind. Then the outer limit, well, the game with the outer limit is trying to maximize the greenhouse effect. So usually when we play this game, we use one favorite greenhouse gas, which is carbon dioxide. You could use others. But we use carbon dioxide because this is what we have on all terrestrial planets in the solar system. But you can play the game with others. And actually, that's very interesting to do that. And if you do that, at some point you have one problem, is that making a thicker and thicker atmosphere, you get rid of more and more radiation to space by just scattering to space. But also at some point, because greenhouse effect warms the surface but cools the upper atmosphere, you will have a problem of condensation. If you make the upper atmosphere too cold, your greenhouse gas will condense. And CO2, well, it's already condensed on Mars. So you will have this problem of a competition between a greenhouse effect, the albedo you're creating by putting more gas into the atmosphere, and condensation. Sorry, there is a missing letter. Typically, with CO2, models kind of agree that it's at least at 1.7 AU from the sun, so beyond Mars. Mars is not an habitable planet with the meaning that I put in this word, not because of its location from the sun, but because of other reasons, like, I mean, its geology, its amount of water, its evolution, its size, whatever. But it's not because it's not inside the habitable zone, which tells you that it's not everything to be in this region. It's just necessary condition, but it's not enough. Okay? So what are the limitations of that, or the comments we can make? So it's mainly computed in the literature for this kind of composition, but you could play with mixture of gas and you can try to increase. You will have this problem of condensation though, so you need to have compounds with a low condensation point. There is not there are not big difference between 1D and 3D simulation, except those that I will show later, because usually close to the outer edge, you need a very thick atmosphere, like several bars of CO2. And this thick atmosphere, they make the condition of the surface quite homogeneous. So basically, 1D models are quite okay compared to 3D models when you're addressing this question of the outer edge, except if clouds do play a role. So there was a discussion about CO2 clouds. It's quite debated. It's quite controversial, the greenhouse effect of CO2 clouds. But if they do play a role, of course, you will need 3D models to try to estimate their coverage on the planet. Otherwise, with 1D, you cannot do that. So there are uncertainties because of that. You could play the same game with methane. Methane condenses at much lower temperature, and it's a very efficient greenhouse gas. The problem we have with methane is it's very fragile. It's photolyzed by radiation, and also in this process, it produces, as Hervé showed, a very complex, or let's say very efficient photochemistry that produces hazes. And these hazes, they counteract the greenhouse effect by scattering light towards space. But maybe not in all conditions, maybe not with all stellar spectra, so it's something that could be explored further. And if you use a pure H2 atmosphere, you could actually put your planet about anywhere in the universe, as long as it has some internal heat flux. So for instance, you take the Earth, and you put it several bars of pure H2. You don't add anything else, just H2. And you put it in the interstellar medium, where outside it's 5 Kelvin. This internal heat flux of the Earth, that's normally without an atmosphere, gives a temperature of about 30 Kelvin at the surface. In this case, it can give the temperature above the freezing point of water. So it's interesting. In this case, we have no outer boundaries of the habitable zone. You can have your planet habitable everywhere. But that's, I would say, it's a kind of academic case, because small planets, they don't tend to accrete, we think, they don't tend to accrete hydrogen, and also you have to add other compounds. But still, it's an interesting case, and we should keep that in mind. It's interesting. So if you consider the limits of the habitable zone, first you see that it's depending on the rotation of the planet, at least, maybe of other things, but you cannot define it independently of the rotation of the planet. That's a problem. If you look at the habitable zone here, actually it's separated in two regions. There is one that's very tiny, where you just need water. You take a bowl covered with water, you put it there, water will evaporate and make its own greenhouse, self-sufficient greenhouse. It works, you don't need another greenhouse gas. The Earth is not inside this region, although we are very close to the inner edge. We need CO2 to keep us warm. And then you have a region where you need another greenhouse gas. And usually we study that with CO2, but it could be something else. And when you're here, you need several bars of CO2, so hundreds of thousands times more than we have here. So there was this idea for a long time that actually, okay, that's nice, but every position in the habitable zone corresponds to one specific atmospheric pressure and composition. So are we lucky to be here with the right composition to have oceans? And actually, it's never going to happen. What's chance are 1 in a million or what? So basically, if you did this composition, it will work here. But if I take the Earth and I put the Earth here, this is what happens. And that's the real time. It goes very fast. You will freeze the Earth. So, and why does it goes why does this freezing goes so fast? It's because of some process called the ice albedo feedback. The ocean has an albedo of less than 10%, between 5 and 10%. The ice has an albedo of 70, 80%. So whenever the surface of ice increases, the cooling of the Earth increases dramatically. So basically, the Earth is known to have two possible climatic states, two solutions for its condition. One that is cold, which is called snowball Earth, and one that is warm, which is the current state that we have. And the Earth spends most of the time in the warm state, but sometime in the cold state. So it's weird. So this means that we were lucky? No, it cannot be this way, because the sun evolved with time. So there must be some kind of regulation process, because we are here now, and here you have the luminosity of the sun, so it's reduced in temperature. We are here now, but several billion years in the past, it was like 20% smaller, which was equivalent to be farther away in the habitable zone. So let's put the evolution of the sun in the picture, and this is the kind of trajectory the planets would have had within the habitable zone. Of course, the planets, we don't believe the planet moved in the solar system, a bit, but not that much. But in terms of flux, this is how they moved. So actually, at each point, points are separated by 1 billion years. So this question of having the Earth deeper into the habitable zone a long time ago gave rise to this question called the faint young sun problem. fine-tuned sound program is, what happened? How is it possible? And this came to realize that we have some regulation process on Earth that's called the carbonate-silicate cycle. How does it work? Well, carbon dioxide is produced by volcanoes, by activity, and it goes into the atmosphere, but it doesn't remain in the atmosphere for long. Actually, it's just passing through, and it's producing carbonate. It's dissolved into water, and then it produces carbonate. It's reacting with sodium, magnesium, iron, whatever. So you have this chain. So if you freeze the Earth like we just did, and we killed many, many billions of species doing that, virtually, but then we cut this chain, and then we build up CO2 in the atmosphere, because we are not stopping the Earth of degassing CO2. So in about 1 million years, you would get about 1 bar of CO2 in the atmosphere. It's a huge greenhouse effect, and you will unfroze the Earth. And you're back on this. And so it means that actually with this system working, you will adapt, the planet will adapt, as long as it has enough CO2 and that you have this system running, the planet will adapt its amount of CO2 to be close to that. And if you're warming these systems, this process will be more efficient, because chemistry will make this, temperature will make this relation faster. So if you increase the temperature, you will make the disappearance of CO2 from the atmosphere into carbonates faster. So there is a very nice regulation here. So we can explain that. And it's good for our definition of the habitable zone. It means that as long as this works on another planet, or there is another regulation systems, our definition, it's quite interesting. But then we have other problems. For instance, well, the very period of time when we have signs of water at the surface of Mars is when Mars was outside the habitable zone as we define it now. And that is not solved today. There are models, but it's very debated. Is this water temporary due to geological activity or to impacts, or was it really a dense, warm climate that was steady for millions of years? There are defenders of both views. What I can tell you is, from the climate point of view, we cannot solve that very easily. Having, at this period of time, an atmosphere, we really have to have ad hoc conditions, adding all the possible greenhouse gas, all the possible warming that we can have in mind. So from the atmospheric point of view, I would favor transient episodes, but I don't know really. And another interesting case is that what happened on Venus when the Earth was less luminous? Actually, with these models, well, it was possible to have some hot ocean on early Venus, but it's an even more complex situation, because actually Venus could be tidally locked, could be synchronized if it has no atmosphere. And the question of the rotation state of Venus was discussed a lot, and actually people came to this solution that seems to work, is the fact that, okay, if you have an atmosphere, basically you're going to heat it and produce some thermal winds that will accumulate a bit of mass here in this region. And because the atmosphere has some circulation, you will move a bit this, what's called thermal tide, okay, in this direction. And so the gravitation will apply a torque on the atmosphere, and this torque will be eventually communicated to the core of the planet, so preventing the planet to completely be tidally locked, or to be locked into a different equilibrium, which is not synchronous state. So basically the problem is that, well, Venus maybe, depends on the dissipation, may be tidally synchronized without an atmosphere. And in climate simulation, a synchronized young Venus can be habitable. But then the atmosphere that we need, that we will produce in this habitable state, would desynchronize the planet. So there is some complex feedback that we need to study further. It's not at all trivial. But you have this situation in the past of the solar system where it's possible that you had at the same time 3 habitable worlds in the same system, and exchanging matter, because we have Martian meteorites on the Earth, and there are probably Earth meteorites on Mars and Venus. So it's interesting, although it's not sure. It's sure for the Earth, but for Mars, we don't know if it was really a permanent habitable state or some variations between frozen and liquid. And for Venus, it's completely speculative. We don't know. We have no traces of that. So now let's go to other stars, because the concept of the habitable zone was first thought for the Sun and to understand the difference between Mars, Venus, and the Earth. But then we are interested in what would be the habitable zone around other stars. And then we have to face the fact that all stars are not suns. And if you look at the 400 closest stars that are within 10 parsecs, so about 30 light years, they are distributed this way. So the Sun is here. It's called the G stars. It's completely arbitrary, this classification. Actually, it's completely continuous. It's continuous in terms of mass, radius, temperature, luminosity. So it's increasing this way. And the lifetime is increasing this way. So massive star live for a very short period of time. And it starts to live for a billion years around the F-type. And so the Sun in this type of star is within the few percent population, which is completely dominated by low mass stars. So it will be interesting to see how climate is affected by the change of star. So this was first done by 1D simulation, and we could compute the limit of the inner limit of the habitable zone for different stellar temperatures. So we go from, let's say, massive star that lives for a bit less than 1 billion years to the smallest star that lives basically forever. And this is the kind of variation you have in terms of flux received by the planet. So you could wonder, why isn't the same value everywhere? Why this limit depends on the temperature of the star? Well, it depends on the temperature of the star because it depends on the spectral distribution of the light that arrives to the planet. Because the atmosphere does not interact the same way with UV, with visible, with infrared. So basically what you have here, I will simplify the spectrum of a star by a black body, and that's the kind of radiation that arrives at the top of the atmosphere in wavelength, so from 0 to 3 microns, so in the visible and near infrared. And this is what's reflected. It's for the Earth's atmosphere. So this is the Rayleigh scattering, and these are absorption bands. Okay? But now, if I irradiate the planet with a colder black body, with the same amount of energy, but from a colder star, I will have no backscattering because I have very little visible light, and most of the radiation will fall into regions where molecules absorb. So basically, the albedo, which is 0.3 for the Earth, here will be less than 0.1. So the planet will absorb much more radiation for the same composition. So when you evaluate the inner edge, you know that the transition between habitable and not habitable is a steam atmosphere. It's a lot of water vapor. So you can compute that for a steam atmosphere, and you have the same kind of process. So you can compute that, and you come to that. So this was for 1D simulation, and I show you one example for the Earth. That in one example, I showed you that 3D simulation find that actually the inner edge is closer. So it's just a raw estimate. And I also told you that if your planet is synchronized, always showing the same face to the star, well, then the limit can be pushed much closer to the star. We don't really know yet because models don't agree, but it could be something like that. So there is a huge difference. And it would depend on the rotation set. So around a Sun-like star, planets at about the temperature of the Sun, they have no reason to be synchronized. It would be an incredible luck to be exactly synchronized. So you need tides to synchronize the planet. And this will be in this region, basically. So it could start here, depending on the dissipation and on the time scales that you allow your planet to be synchronized. It takes time. So basically, it's a conservative region. Everything below that, and if it's not on a very eccentric orbit, should be synchronized. So it means that here, the inner edge could be around here. So just with the ends, I could draw roughly a kind of inner edge that would look this way. So it's interesting. But you have to keep in mind that atmospheric tides will not keep planet tidally locked. So this is a question that we have to solve. So Jérémy Lecomte published that in 2015, and he showed that. So this is in gray. So you have the orbital distance and the stellar mass. So the sun is here, and you have M stars. So here is the region where tides do not affect the rotation of the planet. And in all this region, potentially you can tidally lock your planet. But if you take an atmosphere with, for instance, well, it depends also on the composition, but let's say that you take a surface pressure of 1 bar, everything that's on the right of this diagram would prevent the planet to be synchronized. And here, the effect of the atmosphere would not be enough to that. But it depends on the atmospheric pressure. With 10 bars, you would be here. And if you increase the pressure, you come back here because actually there is an optimum in pressure. So it's a very complicated problem, and we are exploring that. It's very complicated. So the CO2 outer boundary of the habitable zone will be around here. An interesting point is that if you go to colder stars, this effect that is called ice albedo feedback on Earth, that increases the cooling whenever you start freezing the planet, no longer works, or works much less efficiently when you go towards cold stars. This is due to the fact, so this bistability of the Earth's climate, the fact that you could have the Earth this way or this way, disappears for low mass stars. For one reason, it's because in the infrared, the albedo of ice and the albedo of liquid water is about the same. So this difference that we have in the visible light disappears, and so freezing the surface does not change the equilibrium temperature of the planet. So you're losing this equilibrium that we have on Earth. And that was very important. If you think about it, the Cambrian period started just after one of these snowball events. So it's interesting to see that these events, these snowball events, they had, whatever the effect, they had some effect on the evolution of life, and they may not be on this planet. So there might be something different there. So one thing that's interesting is that what's the effect of synchronization for, not about the inner edge, but for planets that well within the habitable zone. And we now have examples of that. An example of that not only because we have in the zoology of extrasolar planets, we have plenty, but we have nearby that we will be able to explore with telescopes in the future and to study their atmosphere. We have two cases. One is Proxima. It's a planet that's around the closest stars, and I had to get rid of everything about Proxima in my talk because I will anyway won't be able to finish my talk. So if you have questions for Proxima, I have like 20 slides more, but if you want to eat, don't ask anything about Proxima. And the reason why I eclipsed Proxima b is because there is a system that I liked even better, which is called TRAPPIST-1, and it's further away in the but it's still close. But it has 7 planets, all of them about the size of the Earth, and it has 3-4 of them within the habitable zone. How cool is that? And this system, so if you have the solar system, it's super small, it's super compact. Actually, it's somewhere between Jupiter and its satellites and the solar system. It would be here in the sun. This planet has a revolution period of 1.5 days, and this very, very distant one, 18 days. In terms of insolation, of stellar light they receive, so they would be between halfway Mercury, Venus, and up to the, let's say, the main asteroid belt. And you have several planets that have insolation or installation. I don't know if the word is official, but that would be near those of the Earth. So what happens, because all these planets are supposed to be tidally locked, always showing the same face to the planet. So what happens if you do that? Well, actually doing that, we found that actually it helps. It helps. It increases the region where one planet can be habitable without changing its atmospheric composition. This region that's so tiny for the habitable zone of non-synchronized planet, here you expand it by a lot. So what happens? Here we have simulation for this planet, the planet E, and for different pressure, and the composition is just, in this case, the same as the Earth. So in terms of abundance, it's N2 and CO2 with the same ratio as on Earth, and water is free to go into the atmosphere according to the temperature. And of course, if you have 10 bars, well, you have oceans everywhere. But you can you can have a zero pressure atmosphere. Actually, you can go down to zero and still have an ocean. The ocean is limited by this line, and this is the region that's facing the planet. So, but you need to have a lot of water. If you have too little water, water would evaporate here, condense here, and it's down. The story is finished. But if you have the equivalent of 1 Earth's ocean or more, the water that goes here condensate, pile up on a big ice sheet, but at some points in the ice sheet it becomes liquid again, like on Europa or Ganymede or Callisto. And not very far, because you have the heat flux from these big planets. It's not like an icy moon. So then you have an ocean inside this, if you have enough water. You have an ocean, and the water goes back here, and so you have a cycle. And it's stable. And stable for a big range of insolation. And so we made this kind of diagram where you have the surface water reservoir, so the amount of water you have. In the unit is, sorry, it's meter, but so the Earth's ocean is about 3 kilometers of water. So this is 1 kilometer. So that would be amounts that are larger than the amount we have on Earth. And this is the partial pressure of CO2 in bars. So we have, 1 bar here, 10 bars, etc. And we have different regions for a planet that's synchronized. And so you have this region where actually you're losing all your water to this ice sheet, and you don't have enough water, and everything is lost. You have this region where actually all the water is vaporized, so it's the typical runaway greenhouse, and being in tidally locked doesn't help. But then you have this eyeball planet case where you have always an ocean on the substellar region, and you can see that if you have enough water, it's independent of the amount of greenhouse gas that you have. So you have another region that you can call if there is enough water, then it must be liquid zone. It's a long name, but then it's huge. It's huge. It's actually all this region. So sometimes having a synchronized planet is cool, sometimes not. Because now if you look at the outer planet of this system, and you simulate that with a pure nitrogen atmosphere and water, but at this temperature, water won't do much. And you look at the coldest temperature that you get on this synchronized planet. Usually, in most of the case, CO2 would condense too. So if you put a lot in your model, because models are fine, you can do whatever you want, but real planets are more complicated. But in your model, if you put, let's say, a 1 bar CO2 atmosphere, then you will get a solution with high surface temperature, or let's say high enough for CO2 to remain there. You have a solution, it works. But if you want to build up the CO2 atmosphere from scratch, it won't work, because every little amount of CO2 you would put in the atmosphere will end in the cold part. You have this region where you can have no cold start without CO2. So let's say, so this is for TRAPPIST-1F. This is the pressure of N2, and this is the pressure of CO2. And this is the region where we have solution. It works. And this is the region where CO2 collapse. But if you start from here, you will end up here. And you will not be able to remain in this region. So there is a problem of being able to keep a CO2 atmosphere or to build it. So you increase the habitable zone this way, and it's not that it's suppressed. You have solutions, but it makes things more complicated. Unless, I don't know, you have a big impact that releases huge amount of CO2, then it's fine, because in one event you will get maybe 1-2 bars of CO2. But otherwise, you have this region that makes cold start difficult. There is another interesting thing in these systems. It's the fact that, like in Jupiter, you have very strong tides that makes orbits circular and planets synchronized with zero obliquity and everything coplanar. That would be if you have isolated planets. But you have several planets, and they gravitationally interact. This is why Europa has a liquid ocean, Ganymede has a liquid ocean, etc. It's because their interaction make their orbit a bit eccentric, and so it allows tides to dissipate. If these bodies were alone, they will find an equilibrium, a tidal equilibrium state with no dissipation. But because so there is a competition between the excitation of eccentricity by the fact that they are very close to each other and they interact, and tidal dissipation. You cannot have zero eccentricity, so you always have tidal dissipation. And this will be the dominant heat source for planet B and C. Planet B in TRAPPIST probably has something equivalent to Io in terms of tidal heating, so about 1 watt per square meter. It's little compared to the amount of light from the star, which is not the case for Io. But for the internal structure, it will have some very, very important role. And it will have also a role for this planet, because the thickness of the ocean, or the thickness of the ice, will be controlled by this amount of heat you get from below. So, and it's not constant, because systems are chaotic, eccentricities exchange and varies, so the heat flux will vary along the time, along the history of the system. A problem we have with these systems, yes?
I was surprised by your previous slide where you say I start with an atmosphere of a bar or something like that. Wouldn't you always start with atmospheres that are like 100 bars?
Yeah, maybe. Bars? Yeah, maybe. You're right. Yeah, I agree. So it's more like if at some points you're losing your atmosphere, you're not getting it back. Okay. But I agree with you that it's, in my, the way I see planet formation, it's more, I agree with you that I would say that you would start with a lot of gas in your atmosphere, and you just have to keep that. I agree with you. So I already showed you something like that. This is the trajectory of the planets due to the evolution of the sun. If I go, for instance, to Proxima b, it's the other way around. The sun, the luminosity of the sun increases with time, but the luminosity of low mass star decreases with time at the beginning and then is stable forever. But this beginning, for instance, could be of the order of 100 million years. And so during 100 million years, your planet here, it's very hot. So it has a kind of Venus conditions, and your water has to be into the atmosphere, and then you cool it. So it's very different from going from here to here. Here you're going from a hot state to a cooler state. And some people say that, well, there is no habitable planets around low mass star, because during this phase, they will lose all their water. Like Venus has no water today, they will lose all their water. Even if you start with two, three Earth oceans. Well, I don't know. And what if you start with 1,000 Earth oceans? And how is the star is not as active as we believe? What if we don't model very well atmospheric escape? And I know that because I'm doing modeling of atmospheric escape, and I don't know actually how to model it. So, but let's observe that. Let's see. And actually, with TRAPPIST-1, which is even worse, it's not 100 million years, it's 1 giga-year. And we are being able to measure the radius, and now we are being able to measure their mass, because they're interacting, planets are interacting gravitationally together, and sometimes they transit, because these are planets that transit in front of the star. Sometimes it's delayed, sometimes it's in advance by maybe 10 minutes, 1 minute, 1 hour, and this depends on the mass. So we have more than 200 transits now for all these planets, and we can constrain the mass quite precisely, actually, and it's really getting better. And so these are the constraints on the different, so it's a messy graph. But let's take only planet B, which is not in the habitable zone, we don't care, but it's the more subjected to atmospheric losses. It's the closest. Well, this is the 1 sigma, 2 sigma constraint on radius and mass. And these are different mass-radius relationship for different composition. And all of those implies a volatile-rich planet. And this volatile cannot be H2. First, for theoretical reasons, we have difficulty to build them, but also we observe that with Hubble, and we can fairly well discard the idea of having an envelope of hydrogen. So, well, then pick your favorite volatile, but I would say water is quite it's a very likely one, not alone, probably with CO2, whatever. So we have volatile rich planets. So, and we have a volatile rich planet that's very close to a star, and a planet that has a very hot history, according to stellar evolution models, around probably very active star. So how is it possible to have, maybe it started with a lot of water, because the estimates in terms of loss of water are maybe 10 Earth oceans. But the Earth has 0.1% of its mass of less in water. Europa, I don't know, it may be 30%, I don't know. Or comets, sometimes it's 50%. So it could be much richer in water. In this case, it would be something like 100 times more than the Earth. So you can afford to lose 10 Earth oceans. Maybe that's the solution, we don't know. But there are uncertainties on these constraints. Maybe we are overestimating the radius. There might be some systematic, so let's observe. Let's look at their atmosphere. And I still have 15 minutes or more, right? Okay. So we know how to look at exoplanet atmosphere, but at the moment we can only do that for big hot planets. So how do we do that? So we usually do that when planet transits. So here you have a light curve. So you're observing a star that has a planet, and this planet is crossing the disk of the star every orbital period, doing that. Pim. So you can observe that at different wavelengths. And what does it tell you? So if you have no atmosphere, well, basically, the decrease in luminosity will not depend on the wavelengths. It will be, for instance, if it's 1%, it will be 1% in the UV, in the visible, in the infrared. If you have an atmosphere, this atmosphere is not as transparent in different wavelengths. So for instance, if you have water in the atmosphere, it will be very opaque in the water bands and more transparent outside. So your planet will look bigger if you're looking in a band where water absorbs, and smaller if you look where it's quite transparent. So we already did that for exoplanets. We found the water vapor in 2007. Now we also found methane, CO2. But big Jupiters or big Neptunes, very hot, like 2000 Kelvin, so not really habitable. Another way to do that, it's when the planet disappears. Here, boom, it disappears. Oh, this gives you the 0 point for the stellar luminosity. So then you can go back to when you saw the planet, just before or just after, and you can make the difference. And here is the emission or the reflection from the planet, and you can do that at different wavelengths, and you can make a spectrum of the planet. We did that already for big planets. We can also zoom in this small variation here. So here during the transit, the planet shows you its night phase, and just before or after the eclipse, it shows you its day hemisphere. And this one is hotter than this one. And if you look in the infrared, what you see here is the difference in temperature between the day and the night, which is sometimes has to do with the circulation and the climate. So it's interesting. There are things we can learn about planetary atmosphere. But at the moment, so it's an example of, and we can add up all these techniques. This was done with Hubble, with the same instrument, a new wide field camera. And this was done for the same planet in transmission, so probing the limbs of the atmosphere like that, and in emission at different points, not just here. You can see what we call the phase curve. We can see how it varies along the path of the orbit. So we can have, by very different methods, ways to probe and to confirm or to study the atmosphere of planets. But we do that typically for hot Jupiters around sun-like stars, something like that. And this would be at scale the Earth. And not only, even the transit of the Earth around the sun is very difficult to get and to measure. Imagine the atmosphere signature. It's not achievable for a long time, and maybe never, I don't know. So one idea that we had a long time ago with some colleagues is to, well, let's shrink the star. We know we are interested in planet of this size and this temperature. This is the definition of a habitable planet, our definition. We cannot change that, but we can shrink the star. Let's shrink the star and make it as small as possible. And this is the smallest you can get. It's TRAPPIST-1 type stars. And you end in the situation that's, when it comes on the screen, I dare to click because I'm afraid that if I click, I will go to the next one. Let's try. Oh no, it's fine. So then you're exactly in the same condition as for your hot Jupiters, but for an Earth-like planet at the Earth's temperature. So you can probe that, not with the instruments that we have now. So first of all, you can detect these planets with ground-based instruments. TRAPPIST-1, actually, the name TRAPPIST is the name of this telescope in Chile. This is the telescope that discovered this system. But then to probe the atmosphere, so we did that with Hubble, and we were able only to discard hydrogen-rich atmosphere, like on Jupiter, Neptune, etc. To probe smaller, heavier atmosphere made of CO2, nitrogen, even water vapor, we need these big things called James Webb Space Telescope that's delayed, and that costs a awful amount of money. But just if one day someone goes into the controversy of the money, just tell them that the money stays on Earth. Even if these things explode in space, the money always stays on Earth. Just change hands and change industries and whatever. That's always something to remind to people. Maybe we are not well organized with public money, but the money always stays on Earth. One thing we haven't discussed, actually we are finding a lot of planets that are not on circular orbit, eccentric planets. Not small eccentricities. Well, some are circular, some have small eccentricities, but some have quite strong eccentricities, like you can see here. And some could be in the habitable zone. So these are bad examples in terms of habitability because these are giant planets. So because with the techniques that we have to find terrestrial planets, small planets, transit, we cannot estimate the eccentricity. The only way to estimate the eccentricity by transit is if we are able to measure the eclipse also, which is very difficult at the moment. So the only examples where we are sure that we have strongly eccentric orbits are mainly giant planets. But there is no reason for not having planets that are sometimes in the habitable zone and sometimes outside. So the first approximation you can make is to average the flux they receive. And we can take an example. So there is one, so let's say there is one planet called Gliese 667cc that if you take the average flux and if you take an atmosphere exactly like the Earth, will give you exactly the same amount of energy that's absorbed by Earth's atmosphere. Everything is different. The albedo is different. The flux is different. You have this term that's due to the eccentricity. So two planets that have the same average orbital distance, they don't have the same average flux. You have to add this term. So the more eccentric, the more flux you receive. So you have this planet that receive exactly the same flux, but that will have very strong variation. Something like 0.3, 0.4, 0.5. So you will have this planet very close to the star and very far away. So if you look at what happens to a planet like that, actually it's very different whether your orbit is like the one of the Earth of about 1 year, or like this one of 2 weeks. Sorry, 4 weeks. Because you will spend more time, in this case, with increased insolation and decreased insolation, while you will average things out easier this way. So I did some small calculation in 1D, and actually there is a paper by Emmeline Beaumont who did that with real 3D models. And basically this is what happened. So if I take the Earth, this would be the variation. So I increase the eccentricity of the Earth, and I put it a bit farther away in order to have the same average flux as the Earth today, in order to be able to compare. And I put it this eccentricity, and that would be the kind of variation I would get. And it's 1D, so I have no ice albedo feedback, but probably here I could start to freeze the Earth and trap it into an icy planet, because I have very wide variations. For this planet, because it's only a 28 days period, well, they don't have time to change. I mean, the inertia of the ocean, the inertia of the atmosphere, make it difficult for the planet to adapt to be in equilibrium with the radiation. So it will react to an averaged flux with very small variations. So that's interesting. Another important thing that we are not going to discuss, but I think it was discussed a lot the first day, is, well, it's fine to be inside the habitable zone, but you need to have water. In order to discuss whether it's liquid or not, you need to have water. And what do we know about the composition of planets? So we had some hints about TRAPPIST-1 that we need to confirm, but otherwise we don't really know whether the Earth is water-rich or water-poor. And for a long time, well, we were saying, well, the Earth got the water from water-rich asteroids that are quite far away from the Earth. So, and if you look at where we expect ice to be in a protoplanetary disk, of course, this snow line is moving. It's not constant in time, but basically, you get it farther away from the habitable zone when you decrease the stellar mass. So there was this idea that maybe planets around low mass stars would be less water rich than the Earth. This was completely changed recently on the theoretical point of view, because basically the idea is that anyway this region is dry everywhere, and what you get is water rich planetesimals from the outer part of the system. And this would work in all the cases except if some giant planets block it. In this case, you have a much less efficient delivery of water on your planet. And I'm sure that Alessandro Morbidelli and Sean Raymond showed you stuff in more detail like that. So it means that, well, some of the ideas that we had in mind, like, well, the Earth is a water-rich planet. Well, maybe the Earth is quite a dry planet. But then I don't know if it's good or bad. Maybe it's bad to have 100 times the amount of water the Earth had. I don't know. So there are plenty of things that I have not discussed in this talk and that are important for habitability. So there is room for several talks like that. Well, I haven't discussed organic prebiotic chemistry or conditions for the emergence of life, but other people did. I haven't discussed impacts, how impacts are going to change in these systems, how dependent are they from giant planets and the architecture of the planetary systems. I don't know. What about tectonics? I show you this carbonate-silicate cycle. It's very important, but it has to do with tectonics somehow. It has to do with the size of the planet. It has to do with its composition. How different is it going to be on other worlds? I have not discussed obliquity, seasons, things like that, which are important. I have discussed just a bit, but not in detail, stellar activity, extreme UV, stellar winds, and in a related way, magnetic fields. So sometimes you will hear, I have seen that in textbooks in schools, that it's important to have a magnetic field, to have an atmosphere and life. I don't know where this idea came from, but Venus has no magnetic field and it has a 100 bar atmosphere. So keep that in mind. So it's probably important for some cases, but it's not always important. But we could have discussed that it has some importance. Moons, what about moons? Some people say, yeah, you need a moon because you need to stabilize the obliquity of the Earth. No, you don't. Depends on the case. Actually, if you remove the moon from the Earth, maybe it will be stable. It depends on the rotation rate you give the Earth. And you don't know what rotation rate the Earth would have without a moon. So you don't know. And having moons, but being a moon, being an icy moon, being a moon around a giant planet that's inside the habitable zone, like Pandora, right, in Avatar. So we know, by the way, that there is no Pandora in Alpha Centauri. And James Cameron is really pissed about that. He had very bad advisors before. But he changed advisors and the new ones are better. We didn't discuss multiple stars, the fact that you can have one planet around two stars, and you can have one planet around a star that has also another stellar companion. These cases have been discussed in the science fiction a lot, very well, but not much in science. A bit, but not much. We didn't discuss the influence of the galactic environment. Is it better to be where we are in the galaxy? What about supernova, gamma ray bursts? Are there regions in the galaxy that are more favorable or more threatening? And what about other galaxies or galaxies billions of years in the past or billion years in the future? These are things I haven't discussed, and because I would not do very good work discussing some of these points. But if you have questions, well, ask me, and thank you very much for your attention and welcoming question.